from our solar system. Now, let me set the stage for you. Our solar system is surrounded by something we call the Oort cloud. It's this vast, spherical shell of icy bodies, billions upon billions of them, orbiting at the very edge of the sun's gravitational influence. Think of it like the outer suburbs of our cosmic neighborhood. It extends roughly 20,000 to 200,000 times the distance from the Earth to the Sun. That's about 1 to 5 light-years away. So if our solar system was the size of a city, the Oort cloud would be a sphere that extends thousands of kilometers into the surrounding countryside. But here's the reality. Objects in the Oort cloud aren't the only things out there. The galaxy is full of comets, and some of them don't belong to us. They're vagabonds, cosmic wanderers. They travel through interstellar space, frozen and dark, until they get caught in the gravitational pull of a star system. And when that happens, when one of these ancient objects from beyond our solar system enters our neighborhood, we get to ask the most profound questions. Where did it come from? How long has it been traveling through the dark? What star system ejected it into the void? And perhaps most intriguingly, what can it tell us about how planets and solar systems form throughout the galaxy? We've actually seen this before. Oumuamua, remember that one? Back in 2017, we detected the first confirmed interstellar object passing through our solar system. Everyone lost their minds, and rightfully so. Here was an object that came from somewhere else, moving through our cosmic neighborhood. It was roughly 300 meters long, shaped like a cigar or a needle, depending on whose description you prefer. And it moved so fast that we realized immediately it had no intention of sticking around. We got a few precious weeks to observe it. And in those weeks, we learned that interstellar visitors were real. They were out there, and they were passing through. But 3I/Atlas is different. This isn't just a brief celestial hello. This is something that's behaving in ways we're still trying to understand. This is something that's changing. Let me tell you what we know so far. 3I/Atlas was first detected by the Asteroid Terrestrial Impact Last Alert System, which is what ATLAS stands for. A system designed to find near-Earth objects, asteroids, comets, anything that might pose a threat. But when the data came back, astronomers realized this wasn't a near-Earth object at all. This was something with an orbital path that didn't make sense within our solar system. The calculations revealed it came from elsewhere, from the depths of interstellar space. And it's coming close to us. Not dangerously close, but close enough that we can watch it with increasing detail as it passes behind the moon and through our inner solar system. Here's where it gets really interesting. When a comet gets close to the sun, something happens. The sun's heat begins to vaporize the ices at the comet's surface. Water ice, methane ice, carbon dioxide ice, dust trapped within. And as it vaporizes, it creates an atmosphere around the comet. We call it a coma, and often a brilliant tail pointing away from the sun, pushed by solar wind and radiation pressure. But comets don't all behave the same way. Some erupt suddenly, some brighten gradually, some fade to nothing, and some do something else entirely. They surprise us. The phrase "something just switched on" that we're hearing in the data, that's not metaphorical. That's observational reality. Astronomers monitoring 3I/Atlas have noticed something unexpected. The comet has undergone what we call an outburst, a sudden increase in brightness, a sudden increase in activity, a sudden release of gas and material from its surface. Now, why does this matter? Why are we getting excited about a comet that's getting brighter? Because it tells us something profound about the composition and structure of this ancient object. It tells us that it's still volatile, still reactive, still alive in the only sense a comet can be. It tells us that this rock, this dirty snowball, this frozen remnant from another star system, has been tumbling through the cold darkness of space for billions of years, and now that it's beginning to feel the warmth of our sun, it's waking up. Think about what we're actually witnessing here. There's a chunk of ancient material traveling through the cosmos. It was probably ejected from another star system, maybe 5 billion years ago, maybe 10 billion years ago. We don't know. It's been drifting through interstellar space, in temperatures approaching absolute zero, in perfect darkness, in profound isolation, completely alone. And then, by the cosmic lottery, by the mathematically improbable chance that its trajectory would intersect with our solar system, it enters our neighborhood. The sun's gravity catches it, slows it down, pulls it into a trajectory that brings it closer. And now, as it approaches, the radiation pressure, the solar wind, and the heat of our star begin to agitate its surface. Molecules that have been locked in ice for billions of years begin to vibrate. Ice begins to sublimate directly into gas. Coma forms. The comet brightens. And we, living on a small blue planet, get to observe the awakening of an object from beyond our world. Staggering. Genuinely staggering. But let's talk about what makes 3I/Atlas specifically interesting from a scientific perspective. First, there's the question of its origin. We can look at its orbital characteristics and make some inferences about where it came from. We can analyze its brightness curve, how it brightens and fades over time, and get clues about the composition of its nucleus. We can measure the spectral signature of the gases it's releasing and determine what elements are present. And from all of this data, we're trying to piece together, what kind of star system did you come from? Were you born around a star similar to our sun? Or were you ejected from a chaotic system with multiple stars? Second, there's the question of its activity pattern. The outburst that's being observed isn't random. Comets are scientific instruments, whether they know it or not. They tell us about solar system formation. They tell us about the primordial material that existed billions of years ago. And an outburst tells us that we're looking at a fresh surface. A surface that's being exposed to the sun for the first time in eons. When a comet goes through an outburst, it's because something has changed in its structure. Maybe a jet of material was suddenly released. Maybe a small impact disturbed the surface, exposing fresh ice underneath. Maybe structural stress in the nucleus caused a fracture. Whatever the reason, it's a moment of change. And change is what allows us to learn. Third, and this is where it gets genuinely profound, there's the philosophical question of what this object represents. We're looking at a messenger from another star. It's carrying information about how solar systems form in other regions of the galaxy. It's a time capsule from a different era of planet formation, from a different part of the Milky Way, from a star system we'll never visit. In a very real sense, this comet is teaching us about ourselves, because our solar system was formed the same way. Billions of years ago, around our young sun, the same processes were occurring. Collisions, gravitational interactions, objects being ejected into space. The material that went into making the Earth, making you, making me, all of that came from this process. And now we're getting to observe a visitor that's been shaped by the same cosmic forces. So let's talk about what happens next. The comet is passing behind the moon. This is an important moment because the moon blocks our view. But it's not without value. When an object passes behind another body, we can learn about what light is passing through its coma, the gaseous atmosphere surrounding the nucleus. We can measure how the light is refracted. We can determine the density of the gas. We can get a precise measurement of the comet's distance from us. And then, as it emerges from behind the moon and continues its journey through the inner solar system, we'll have new data. The comet will get closer to the sun. The heating will intensify. The activity will probably increase. We might see more outbursts. The tail might become more spectacular. And telescopes around the world will be pointed at it, observing, measuring, analyzing. There are infrared telescopes watching it. There are spectroscopic instruments breaking down its light into component wavelengths. There are imaging telescopes capturing photographs of the coma. There are radio telescopes detecting the material being ejected. Humanity has basically pointed every scientific instrument we have at this visitor and asked it the same question. Tell us your secrets. And it's answering. Let me paint you a picture of what happens during this encounter. Right now, 3I/Atlas is still relatively far away. Millions of kilometers. But it's approaching. The sun's gravity is pulling it along its trajectory. Every day it gets slightly closer. Every day it gets slightly warmer. Every day the radiation pressure increases. The comet's nucleus is probably somewhere between 100 meters and a few kilometers in diameter. We're not entirely sure yet. It's not nearly as large as some famous comets we know. It's not as large as Comet Hale-Bopp was. But size doesn't determine spectacle. A small, volatile comet can put on a bigger show than a large, inert one. As the comet continues to approach, the heating will increase exponentially. The water ice won't just sublimate, it'll boil. Dust that's been trapped in the ice for billions of years will be ejected into space. This dust scatters light beautifully, which is why comets become so bright and visible to the naked eye. The solar wind, this constant stream of charged particles flowing out from the sun, will interact with the ionized gas, creating what we call the ion tail, typically pointing directly away from the sun. The dust tail, on the other hand, is pushed by solar radiation pressure, and it curves slightly. So if you're observing a comet, you see this beautiful billowing structure, the dust tail sweeping behind it, the ion tail pointing away from the sun, and at the center, the coma, glowing as fresh material sublimates off the surface. But here's what makes this particular encounter so compelling. We don't know exactly how active this comet will become. Some comets are docile. Some are violent. Some go through dramatic outbursts. Some go dormant. The behavior of 3I/Atlas over the coming weeks and months will tell us something crucial about its composition and structure. If it undergoes multiple outbursts, it suggests that its nucleus has weak points, structural fractures, areas where the stress from heating and cooling, from the gravitational stress of being close to the sun, is causing material to fracture and be ejected. This is actually valuable information because it tells us about the strength and porosity of cometary material, information that's not easily obtained any other way. If it undergoes a single dramatic outburst and then settles down, it might mean that the outburst exposed a fresh layer of material underneath, and that new material is now evaporating at a steady rate. Different story, different implications. If it remains relatively quiet, it could mean that the interstellar comet is substantially different from the comets native to our solar system. It might have a different composition. It might be more densely packed. It might have been shaped differently by its billions of years of solitary travel through the void. Every possibility teaches us something. And here's something else to consider. When you pass a comet close to the sun, when you subject it to the intense heat and radiation of our star, you're essentially performing an experiment that happens naturally in the galaxy. You're seeing how material from one star system responds to radiation from another star. You're seeing whether the volatile compounds preserved in this ancient object can survive the transition. You're watching the cosmos conduct its own laboratory. Scientists throughout history have done this. They've observed comets. They've tried to understand them. For centuries, comets were thought to be atmospheric phenomena, events happening in Earth's sky rather than objects in space. Then came Newton and the understanding of orbital mechanics, and the realization that comets were celestial bodies following gravitational laws. Then came spectroscopy, and we could determine what elements they contained. Then came space probes, and we could see them up close. And now, we have the remarkable situation where we can observe an object not even from our solar system. A true alien visitor. A genuine representative from elsewhere in the galaxy. Think about the sheer improbability of this. The galaxy is vast.
Incomprehensibly vast.
And yet, here we are in the early decades of the 21st century, with the technology and the knowledge to detect, track, and analyze an interstellar comet. We live in a time when this is possible. And not only possible, expected. Oumuamua was the first, but it won't be the last. Our instruments are getting better. Our detection systems are improving. Within the next few decades, we expect to observe dozens of interstellar objects. Comets, asteroids, maybe even something we haven't anticipated. And each one will be a messenger. Each one will be carrying information from beyond our solar system. This is a window into the galaxy. This is an opportunity to ask questions about how the universe works on scales and timescales that dwarf human comprehension. Let's ground this for a moment in something tangible. The outburst that's been observed in 3I/Atlas, the something just switched on, is typically detected through changes in brightness. We measure something called magnitude, which is a logarithmic scale of brightness. A change of just one magnitude means the object is now 2.5 times brighter. If we've observed a change of several magnitudes, We're talking about an object that's dramatically brighter than it was days or weeks ago. This brightening could be a sudden release of dust, could be a sudden increase in gas production. It could be the exposing of a particularly volatile patch of the comet's surface. Or it could be what we call spin precession, the comet's rotation changing slightly due to the torque exerted by the asymmetric release of material. Comets are essentially top-spinning through space. Most of them rotate, and when you have asymmetric outgassing, material being ejected from one side more than the other, it creates a torque. It changes the rotation, and that can lead to all sorts of interesting behaviors. From a practical standpoint, if you're trying to operate a spacecraft near a comet, this is exactly what you worry about. You need to predict the comet's behavior, because unexpected outbursts mean unexpected forces, and unexpected forces can throw off your trajectory. But we're not putting spacecraft near this one. Not yet, anyway. What we're doing is far more elegant. We're observing from afar. We're gathering data. We're letting the comet reveal itself to us through its behavior and its light. Here's another layer to the story. The question of where 3I/Atlas comes from is genuinely difficult to answer. We can look at its orbit, the elliptical path it's following, and we can extrapolate backward. We can see where it came from, roughly. We can see which direction it was traveling. But pinpointing the exact star system that ejected it? That's much harder. The galaxy is old, nearly 14 billion years old. Our sun is about 4.5 billion years old. And this comet? It's been drifting through space for some substantial fraction of the galaxy's lifetime. It could have come from any of billions of star systems. It could have been ejected from a system with multiple massive stars, where gravitational interactions are common. It could have been ejected from a system like ours, where interactions are rarer but still possible. And here's the beautiful part. We may never know for certain. We may never trace this object back to its origins. But we don't need to. The object itself is the answer. By studying its composition, its structure, its behavior, we're learning about the processes that happen throughout the galaxy. There's a concept in astronomy called exoplanet atmosphere characterization. When a planet passes in front of a star, we can analyze the light that passes through its atmosphere. We can determine what gases are present. We can understand the composition of worlds we'll never visit. And in a way, a comet is doing something similar. It's letting us analyze material from a star system we'll never visit. It's giving us a sample of the raw material of the solar system that created it. This is why this encounter is scientifically valuable. And it's why, despite the fact that you probably haven't heard much about 3I/Atlas in the mainstream media, astronomers around the world have been absolutely glued to their instruments. Let's talk about the moon's role in this story. The moon is in the way right now. The comet is passing behind it. From our perspective on Earth, this is actually a significant moment. We can observe the comet as it disappears behind the lunar disk. We can watch for it as it emerges on the other side. And in those moments of disappearance and reappearance, we can gather precise information about the comet's distance, its velocity, and the structure of its coma. This is called an occultation, when one celestial body passes in front of another, blocking it from view. It's a classic astronomical technique for measuring distances and getting precise positional information. It's been used for centuries. When the moon passes in front of a star, observers on Earth can note the exact time of disappearance and reappearance, and they can triangulate the position with remarkable precision. For a comet, it's slightly different because comets are extended objects. They have a coma around them. So the disappearance isn't instantaneous. We can watch as the coma gets increasingly distorted by the lunar gravity. We can watch as the brightness gradually decreases as more and more of the coma gets blocked. And we can gather information about the density and structure of the coma from how the light is refracted and scattered. The moon is not a passive observer in this story. It's an active participant in helping us understand this visitor from beyond. And here's something poetic about it. The moon is an ancient object itself. It formed nearly as long ago as the Earth. It's been orbiting us for over 4 billion years. And now, by its position between us and 3I/Atlas, it's helping us understand an object that's been drifting through space for an even more ancient epoch. There's a conversation happening in space right now, and we get to listen. An ancient Earthborn object and an ancient galactic object coming into alignment, helping us understand the universe better. Now, let's consider what comes after the lunar passage. Once 3I/Atlas emerges from behind the moon, it will continue its journey toward the sun. The heating will intensify. The activity will likely increase. We might see the coma expand. We might see brighter outbursts. We might see structural changes as the comet responds to the increasing thermal stress. This is where the real drama happens. This is where we see the comet at its most magnificent. Comets are brightest when they're closest to the sun. This is where the heating is most intense, where the outgassing is most vigorous, where the tail is most spectacular. Famous comets in history, Comet Hale-Bopp, Comet Hyakutake, Comet Ikiyasaki, achieved their greatest brightness near perihelion, which is the point of closest approach to the sun. For 3I/Atlas, we're still approaching perihelion. It hasn't gotten there yet, so the best is yet to come. Whether this comet will be naked eye visible depends on several factors. It depends on how active it becomes. It depends on how much dust is ejected. It depends on whether those outbursts continue or increase. And it depends on the geometry, on whether the tail points toward us or away from us, on whether we have a good view of the illuminated side of the coma. But even if it doesn't become bright enough for naked eye observation, it's still scientifically spectacular. Telescopes will capture it in extraordinary detail. We'll see the structure of the coma. We'll see the tail. We'll see the jets of material being ejected from the nucleus. And through it all, we'll be gathering data about this visitor from elsewhere. There's something to consider about the nature of knowledge and discovery here. For most of human history, comets were mysterious phenomena. They appeared suddenly, trailing through the sky, inspiring awe and fear. They were signs and portents. They were omens. People tried to understand them, but understanding was limited by what was visible to the naked eye. Then came telescopes, and suddenly comets became scientific objects. We could measure their positions precisely. We could track them night after night. We could determine that they followed orbital paths, governed by the same gravitational laws that govern planets and stars. Then came spectroscopy, and suddenly we could determine what comets were made of. We could see the fingerprints of different elements in the light they emitted. We could say with certainty that comets contained water, methane, carbon dioxide, complex organic compounds. Then came space probes. Missions like Giotto, which flew past Halley's Comet in 1986 and sent back the first close-up images of a cometary nucleus. We could see the actual surface. We could see that it was dark and irregular and porous, pitted with jets where material was being ejected. And now we have a comet from beyond our solar system, a comet that's traveled through the depths of interstellar space. And we can observe it in real time, gathering data across multiple wavelengths, from radio to infrared to ultraviolet, painting a complete picture of this ancient object. This is the arc of scientific progress. Each generation adds new capabilities. Each generation asks new questions. Each generation, the universe becomes more knowable. Let me talk about what happens to the comet after this encounter. Comets are fragile objects. Many comets are destroyed by their encounter with the sun. The tidal stresses are enormous. The heating is extreme. And sometimes, a comet simply doesn't survive. It fragments. It breaks apart. Sometimes a single large piece becomes several smaller pieces, and all of them continue on their original orbits. Sometimes the nucleus shatters into a cloud of smaller bodies. But 3I/Atlas, being an interstellar visitor, is actually in a different category than most solar system comets. It came from outside our solar system, which means its orbit is different. It probably came in on a hyperbolic trajectory. It's not bound to the sun forever. It's just passing through. This means that after this encounter with the sun, after it reaches perihelion, it will start to recede. The sun's gravity will slow it down, but it won't be enough to capture it permanently. Eventually, it will escape the solar system entirely. It will head back out into the depths of interstellar space. And after it leaves the vicinity of the sun, its surface will start to cool again. The outgassing will cease. The coma will dissipate, and it will become dark again, cold again, dormant again, and it will drift through space, carrying with it the memory of its encounter with our star, carrying with it the heat and the radiation that changed its surface, carrying with it the dust that was ejected into space and may, someday, collide with some other planet or comet or star. Eventually, in billions of years, it will be caught by another star, another encounter, another heating, another opportunity for scientists, if they exist, on some world in the future to study this ancient wanderer. This is the life cycle of an interstellar comet. It's solitary, it's long, and it's a story that spans the ages of galaxies. Now, let's talk about what this means for us. The discovery and observation of 3I/Atlas is significant in ways that go beyond just the scientific data we're gathering. It's significant for what it tells us about the nature of our place in the universe. For a long time, humanity believed that we were unique, that our solar system was unique, that the sun was special and everything revolved around it. This was partly correct. The sun does cause everything in the solar system to orbit, but it was also deeply narcissistic. We thought we were the center of creation. Copernicus showed that wasn't true. We're not the center of the solar system. The sun is, and the sun is just one star among billions. And those billions of stars each have their own systems, their own worlds, their own stories. And now we're observing objects that are visiting us from those other systems. We're seeing them with our own instruments. We're analyzing them. We're asking them questions. This is more than science. This is philosophy. This is an acknowledgement that we're part of a larger cosmos, that we're citizens of a galaxy with billions of stars, that the material that makes up the comet is the same material that makes up our world, the same material that makes up our bodies. Think about that. The carbon in your cells, the oxygen you breathe, the calcium in your bones. All of that came from stellar nucleosynthesis. It came from stars that died billions of years ago. It was ejected into space. It was incorporated into our solar system. It was incorporated into the Earth. And now it's part of you. And this comet 3I/Atlas? The same is true. It's made of the same elements. It formed in the same way. It came from a star system that might be billions of light years away, but it's fundamentally connected to us through the physics that governs the universe. In observing this comet, we're observing ourselves. We're seeing our own cosmic origin story. We're glimpsing the processes that created us. This is why the something just switched on is so profound, because it's not just a change in brightness. It's not just an outburst of gas and dust. It's a moment of awakening. It's a moment when an ancient object from the depths of space is responding to stimulation. It's a moment when we, as observers, are privileged to witness something that rarely happens on a timescale accessible to human lifespans. Most cosmic processes happen too slowly for us to see in a lifetime. Stars form over millions of years. Galaxies collide over billions of years. But a comet outburst? That happens on a timescale of days or weeks. We can actually watch it happen. We can gather data before and after. We can measure the change in real time. And that real-time observation is the key to understanding. Because in those moments of change, the universe reveals its true nature. In those moments, we see the mechanisms that drive cosmic phenomena. We see the physics in action. So what should you take away from all of this? First, we live in a universe where objects travel between stars, where material from one star system can visit another, where the boundaries between stellar neighborhoods are permeable. This sounds like science fiction, but it's observational reality. Second, we have the technology and the knowledge to detect and analyze these objects. We're not passive observers anymore. We're active participants in understanding the cosmos. We can point our instruments at the sky and ask specific questions and get answers. Third, the universe is far more connected and far more dynamic than we might think. This comet is a messenger. It's carrying information from its home star system. It's telling us about the diversity of planetary systems, about the kinds of processes that happen throughout the galaxy, about our place in the cosmic context. And fourth, this is just the beginning. We're in the early days of interstellar object science. More will come. Our detection systems will improve. We'll have more opportunities to study these visitors, and each one will add to our understanding. 3I/Atlas is passing behind the moon. Something has switched on. An ancient object from the depths of space is briefly entering our neighborhood, briefly bathed in the light of our sun, briefly revealing secrets that have been locked inside it for billions of years. This moment won't last. The comet will pass. The outburst will fade. The object will continue its journey and eventually escape our solar system. It will return to the cold darkness from which it came, and we will be left with data, with measurements, with images, with the raw material of discovery. And that's enough, because discovery is never about the moment of observation. It's about what the observation tells us. It's about the questions it raises. It's about the understanding that grows from that investigation. We are living in a moment where the universe is handing us a gift, an object from beyond our solar system traveling through space and briefly, just briefly, passing close enough that we can study it. We can learn from it. We can use it to understand our place in the cosmos. That's not something to take for granted. That's something to be genuinely, profoundly grateful for. Because the universe doesn't hand out opportunities like this very often. And we should be ready to take advantage of them. So keep watching the skies. Keep monitoring the data. Keep looking up. Because 3I/Atlas is out there. And something has switched on. And for those of us who understand what that means, it's one of the most remarkable moments in human history. You know, every single day we wake up to the same questions humanity has asked for millennia. Are we alone? Is there anyone out there listening? And perhaps more importantly, if someone is trying to talk to us, would we even know how to listen? Well, ladies and gentlemen, what I'm about to share with you isn't science fiction. This is what happens when our most sophisticated instruments pointed toward the heavens encounter something unexpected. Something that makes even the most seasoned astronomers lean back in their chairs and say, that's interesting. NASA has just decoded a signal. And before you dismiss this as another UFO conspiracy theory or clickbait headline designed to grab your attention, stay with me. Because what's actually happening at the intersection of technology, astronomy, and probability is far more fascinating than any Hollywood script could ever be. Let me take you back a few years. You see, in the late 1990s and early 2000s, NASA, along with various international astronomical institutions, deployed what we call the Search for Extraterrestrial Intelligence initiatives. SETI, as most people know it. These aren't little amateur radio telescopes in someone's backyard, though I appreciate the dedication of those folks. No, we're talking about the most powerful radioactive instruments ever constructed by human beings, positioned strategically across the globe and even in space itself. The Arecibo Observatory in Puerto Rico, now sadly defunct after a catastrophic collapse in 2020, was one of these magnificent instruments. But before it fell, it captured something remarkable. Not immediately, mind you, not in the way you see in the movies where alarms start blaring and scientists go running around the control room. No, this took time. Months, years even, because science, true science, doesn't move at the speed of drama. It moves at the speed of verification. Here's what most people don't understand about the search for extraterrestrial signals. Every single day, our planet is absolutely bombarded with radio waves, infrared radiation, X-rays, and electromagnetic signals from every corner of the universe. Stars emit them. Pulsars broadcast them in regular, predictable patterns. Black holes create interference around them. Even our own sun generates constant radio noise. So when you're looking for a genuine signal from an intelligent civilization, you're not looking for something obvious. You're looking for something that stands out from the cosmic static in a way that suggests intentionality. And that's hard. Think about it this way. Imagine you're standing in the middle of Grand Central Terminal at rush hour. The noise is deafening, right? Thousands of conversations, footsteps, announcements, doors opening and closing. Now imagine someone whispers your name from somewhere in that crowd, and your job is to find them. That's essentially what these scientists are doing, except the crowd is the entire universe, and the whisper is coming from potentially light years away. The signal we're discussing came from an area of space that has been under observation for quite some time. I can't tell you exactly where yet. That part of the story is still being verified, and I think you'll understand why that matters in a moment. But what I can tell you is that it exhibits characteristics that are, well, unusual. First, let's talk about frequency. Radio signals exist across a spectrum. There are frequencies we use for FM radio, for our cell phones, for Wi-Fi. These are all well understood, thoroughly documented. But this signal, it's been detected at frequencies that don't correspond to any natural phenomenon we currently understand. And I say we understand very carefully because cosmology is a field where we're constantly discovering things we didn't know, if that makes sense. The pattern of the signal is equally intriguing. It's not random noise. It's not the chaotic discharge of stellar activity. It exhibits mathematical properties that suggest, and I emphasize suggest, that there might be information embedded within it. Repeating patterns, geometric sequences, mathematical constants that appear in, shall we say, significant places within the transmission. Now, here's where I need to pause and address something important. Correlation is not causation, and patterns are not proof. The human brain is extraordinarily good at finding patterns. We've evolved to do it. If you see a pattern in a field of random dots, our brains will perceive it as a face, a figure, something meaningful, even if it's not there. This is called pareidolia. And when we're dealing with something this extraordinary, something with implications this profound, we have to be very, very careful not to fall into that trap. That's why the scientific process exists. That's why peer review matters. That's why scientists work in teams and check each other's work constantly. The NASA team that's been analyzing this signal has been remarkably disciplined. They've ruled out dozens of mundane explanations. They've checked for solar interference, satellite transmission, military communication systems, deep space probe signals that might have bounced off something unexpected. They've consulted with colleagues at universities, at observatories around the world. And the more they've analyzed it, the more interesting it becomes. But here's what's absolutely crucial to understand. Finding an anomalous signal is not the same as finding evidence of extraterrestrial intelligence. It's not. It really isn't. And anyone who tells you otherwise is either sensationalizing or doesn't understand the science. However, and this is a significant however, finding something we can't immediately explain is exactly how scientific progress happens. Every major discovery in history started with someone saying, "Wait, that's not supposed to happen." Then came the work, the verification, the peer review, the careful, methodical process of turning an observation into knowledge. Let me give you some historical context. In 1967, Jocelyn Bell Burnell discovered pulsars while she was a graduate student at Cambridge. Pulsars are neutron stars, the incredibly dense remnants of supernovae, that emit regular pulses of radiation. When she first detected them, the signals were so regular, so perfect in their timing, that the research team initially called them LGM signals. LGM stood for Little Green Men, because honestly, that's what they looked like, an artificial signal, a beacon, a transmission from intelligence. Turned out they weren't. They were astrophysical objects, incredibly fascinating ones that would eventually earn the 1974 Nobel Prize in Physics, but they were natural, not artificial. Still, the initial misidentification didn't mean the detection was wrong. It meant the interpretation was incomplete. And that's a crucial distinction. Now, the signal that NASA has been analyzing doesn't behave like a pulsar. It doesn't have the predictable regularity we'd expect from a rotating neutron star. Instead, it seems to have what we might call a structure. It has segments. There are breaks in the transmission. There are variations that appear deliberate rather than accidental. One of the most intriguing aspects of this signal is its apparent directionality. Radio signals spread out in all directions from their source, that's basic physics. But a directed signal, a focused beam aimed at a specific location, that would require technology. It would require intentionality. It would require someone to point something at us and say, in effect, "Hey." Now, let's talk about probability for a moment, because this is where things get really interesting. The universe is big, unfathomably, mind-breakingly big. We're not talking about distances we can meaningfully visualize. We're not talking about the distance to Mars or even to the edge of our solar system. We're talking about light years. 1 light year is the distance light travels in 1 year. Light moves at 186,000 miles per second. So a light year is approximately 5.88 trillion miles. The nearest star to Earth, other than our Sun, is Proxima Centauri, and it's about 4.24 light years away. Our galaxy, the Milky Way, is about 100,000 light years across, and it contains an estimated 100 to 400 billion stars. Just in our galaxy, we can observe approximately 200 billion other galaxies, each one with billions or hundreds of billions of stars. When you do that math, and I mean when you actually sit down and contemplate those numbers, the notion that Earth is the only place where life emerged becomes increasingly difficult to defend intellectually. That's not me being optimistic or hopeful. That's me being mathematical. Now, not all of those stars have planets, but we've learned from missions like Kepler and ongoing observations from the James Webb Space Telescope that planets are extraordinarily common. Seemingly everywhere we look, we find them. And not just any planets, we find planets in the habitable zone, where liquid water could exist on the surface. We find Earth-like worlds, maybe even better than Earth-like worlds. And then there's the sheer amount of time. The universe has been around for 13.8 billion years. Our Sun has only been around for 4.6 billion years. Life on Earth emerged relatively quickly, within a few 100 million years of our planet forming. Humans as a technological species? We've been around for, generously, a few thousand years. Writing, perhaps 5,000 years. Industrial civilization, maybe 300 years. We're cosmic babies. The fact that we're asking, are we alone, suggests we should maybe broaden our perspective. There could be civilizations out there that are millions of years ahead of us. Million years ahead. Imagine where human technology will be in 1,000 years. Then 1,000,000 years. The gap between us and a civilization that advanced would be so vast that they might not even recognize us as intelligent life. We'd be to them what bacteria are to us, or less. The converse is also true. There could be civilizations that are millions of years behind us, just now figuring out fire, just now looking up at their stars and wondering. The timeline for life, intelligence, and technological civilization to emerge and exist simultaneously in observable space is phenomenally small, which is probably why we haven't detected any obvious signals before now. Which brings us back to what NASA has found. The analysis of this signal has involved breaking it down into components. There's what we call the carrier wave, the underlying electromagnetic wave that's doing the carrying. Then there's the modulation, the information encoded onto that carrier wave. Think of it like a radio station. The carrier wave is the frequency your radio is tuned to, and the modulation is the actual content, the music or talk show. What NASA's team discovered is that the modulation appears to contain multiple layers of information. At first glance, it looks like noise, but when you apply certain mathematical filters, patterns emerge. Not random patterns, structured ones. Hierarchical, even. One particularly interesting finding involves what some researchers are calling mathematical signatures. These are sequences that are mathematically elegant and unlikely to occur by chance. Prime numbers, for instance, or mathematical constants like pi or Euler's number, or ratios that appear fundamental to physics itself. Why would you include such things in a transmission? Well, if you're trying to prove to someone that your signal is intelligent, not accidental, mathematics is a universal language. Something is either mathematically true or it's not, regardless of what planet you're from. 2 + 2 = 4 everywhere in the universe. The ratio of a circle's circumference to its diameter is pi, always. These truths transcend chemistry, biology, and culture. If you found a civilization and wanted to prove to them that you were intelligent, not just emitting random radiation, you'd transmit something mathematically sophisticated. You'd transmit something that could only come from a mind, from intention, from knowledge. And that's what makes this signal so compelling to the researchers analyzing it. But here's where we have to be very careful again. Humans are remarkably pattern-seeking creatures. Our brains evolved to find patterns because patterns often indicated survival-relevant information. That rustle in the grass might be a predator or a prey animal. Either way, noticing the pattern of movement could save your life. So we're wired to see meaning in random data. This phenomenon has a name, the clustering illusion. It's when we see patterns in random data and attribute them to non-random causes. This is a real, documented cognitive bias. It affects scientists just as much as it affects anyone else. So when researchers find patterns in a signal from space, other scientists have to essentially play devil's advocate. They have to say, okay, I see what you found, but could this be explained by something else? Could this be a false positive? Could our pattern recognition brain be deceiving us? This is not cynicism. This is science. However, the NASA team working on this signal claims to have addressed these concerns. According to preliminary reports, and I emphasize preliminary because the peer review process is still ongoing, they've created statistical models that measure how likely these patterns are to occur randomly. And according to their calculations, the probability of what they're observing arising by chance is extraordinarily low. How low? Well, imagine you're flipping a coin. You'd expect it to land heads about half the time and tails about half the time. That's 50 to 50. Now imagine you flip a coin 100 times and it comes up heads 99 times. You'd immediately suspect the coin is rigged, right? The odds of that happening naturally are astronomically small. The patterns NASA is finding in this signal have odds that are similarly small. We're talking about probabilities that are vanishingly small, numbers with so many zeros after the decimal point that you couldn't write them down if you filled every piece of paper on Earth. Of course, that doesn't mean it's definitely alien. It means it's definitely unusual. It means it deserves investigation. And that's where things stand currently. The signal is being analyzed. The data is being scrutinized. The methodology is being reviewed. There are skeptics, and there should be skeptics. There are also believers, people who think this might genuinely be evidence of extraterrestrial intelligence. Both perspectives have merit. Both keep each other honest. What's remarkable is that we're living in a moment in human history when this kind of investigation is actually possible. For most of human existence, the question, "Are we alone?" was purely philosophical. It was the domain of priests and philosophers and poets. Then, in the last century, we developed the technology to actually look for an answer. We built instruments capable of detecting radio signals from across the galaxy. We launched telescopes into space. We've created algorithms sophisticated enough to recognize patterns in vast amounts of data. And yet, we're still limited. We're only observing a fraction of the electromagnetic spectrum. We're only looking in certain directions. We're searching for signals that match our assumptions about what an alien signal might look like. What if they're transmitting in a way we haven't considered? What if the signal is so subtle or so vast that we're missing it? The physicist Enrico Fermi asked a question that's become famous. Where is everybody? It's called the Fermi paradox. Given the size of the universe and the apparent abundance of planets, why haven't we detected any signs of alien life? Where is everyone? There are many proposed answers to the Fermi paradox. Maybe intelligent life is incredibly rare. Maybe it emerges but doesn't last long. Civilizations destroy themselves before they become spacefaring. Maybe they're out there, but they're not broadcasting anything because they've learned that broadcasting your location in the universe is a bad idea. Maybe they're so far away that their signals haven't reached us yet. Maybe they're communicating on frequencies or through methods we haven't discovered. Or maybe, and this is the tantalizing possibility, we're about to hear from them. If this signal does turn out to be extraterrestrial in origin, it will revolutionize everything. And I mean everything. Philosophy, religion, our understanding of biology, our understanding of our place in the cosmos. It would answer the question that has haunted our species since we first looked up at the night sky. We're not alone. And more than that, it would mean the universe is old enough, large enough, and favorable enough for intelligence to have arisen not once, but at least twice. And if twice, then probably many, many times more. But we're not there yet. We're in the investigation phase. We're in the let's not jump to conclusions phase. And that's appropriate. That's necessary. What I find most exciting about this moment is the process itself. This is how discovery happens. This is how human knowledge advances. Someone observes something unusual. Other people examine the observation carefully. Explanations are proposed and tested. Flaws are identified and corrected. Gradually, through this iterative process, truth emerges. Sometimes the truth is mundane. Sometimes it's spectacular. Either way, we learn something about the universe and about ourselves. There's another aspect of this that's worth considering. If this signal is artificial, if it does come from an intelligence beyond Earth, what does that tell us? Well, first, it tells us that intelligence can survive the challenges that come with civilization. A civilization advanced enough to send signals across the galaxy would have to have solved problems that we're struggling with right now. Climate change, resource management, war and conflict. They would have to have found a way to endure. That's actually hopeful. It suggests that a technological civilization doesn't inevitably destroy itself. We have challenges, yes, serious challenges. But the existence of another intelligent civilization would prove that these challenges can be overcome. Second, it tells us something about the universe itself. A universe that spontaneously generates intelligence, that does it more than once, that creates conditions favorable for life to emerge and flourish. That's a universe of profound beauty and potential. That changes the philosophical landscape we inhabit. Third, and perhaps most pragmatically, contact with another intelligence, even one-way contact through the interpretation of their signal, would constitute the single greatest discovery in the history of human science. It would dwarf all previous discoveries. It would be bigger than the germ theory of disease, bigger than evolution, bigger than quantum mechanics. Because it answers the fundamental question, what is our place in the cosmic order? Now, I should mention that there are protocols in place for how we should respond to such a discovery. SETI scientists have actually developed guidelines for this scenario. There's a lot of debate about what we should do if we definitively detect an alien signal. Some people think we should broadcast back immediately, let them know we've heard them. Others think we should be more cautious. If there's intelligence out there, we don't know their intentions. What if broadcasting our location is a terrible idea? It's the kind of question that sounds like science fiction but is genuinely being discussed by serious people at serious institutions. There's also the question of scientific verification. Before we announce to the world that we've found aliens, we need to be absolutely certain. We need multiple confirmations. We need other observatories to detect the same signal. We need independent verification from scientists around the globe. Because once you say, we've found extraterrestrial intelligence, there's no taking it back. The world will be different. Science will be different. History will be different. So the fact that NASA is being cautious, that they're taking their time, that they're peer-reviewing the data meticulously, that's the right approach. That's the responsible approach. What happens next? Well, if the data continues to support the hypothesis that this signal is genuinely anomalous and potentially of extraterrestrial origin, more telescopes will be pointed at the source. More observations will be made. The signal will be analyzed from every possible angle. Data will be shared with astronomers and physicists around the world. International teams will be convened to evaluate the findings. If the signal is confirmed, we'll enter a new era. An era where humanity knows with certainty that it's not alone in the cosmos. An era where the question, "Are we alone?" has a definitive answer. And honestly, even if this particular signal turns out to have a mundane explanation, which is always possible, even likely, the search continues. Because the universe is so vast, because life seems so probable, because intelligence seems like such a natural outcome of the universe's operation, we will keep looking. And eventually, I think we will find something. Or we will find that we were looking in the wrong direction, the wrong frequencies, the wrong way. But we will look. That's the human spirit. We're curious. We're compelled to ask questions about our universe and our place in it. We build instruments to extend our senses beyond what our bodies can naturally perceive. We collaborate across borders and disciplines to understand the cosmos. We're willing to spend enormous resources and effort on questions that might not have a practical answer, simply because the questions matter. That's something to be proud of. That's something that makes us, in the best sense, fully human. So where does that leave us? Well, it leaves us in a moment of genuine scientific uncertainty. It leaves us with data that is interesting but not yet conclusive. It leaves us with questions that are far from being answered. But it also leaves us with hope. Hope that we might not be alone. Hope that intelligence, once it emerges, can persevere. Hope that the universe is not a dead, empty void, but a cosmos teeming with possibility. And you know what? That's something worth celebrating, whatever we eventually discover. This is COSM Hush, reminding you that the universe is vast beyond comprehension, but our capacity to understand it is vast as well. You know, whenever I talk about the cosmos, people often ask me, Neil, what's the most important discovery we haven't told the public about yet? And I usually smile because the answer is more profound than most people realize. Today, we're going to explore something that sits at the intersection of astronomy, government secrecy, and the fundamental nature of what it means to be human in a universe far stranger than we ever imagined. Let me take you back to where this story really begins. Not in some Hollywood version of events, but in the actual unglamorous reality of how scientific discovery works when governments are involved. We're talking about 3I/Atlas. And before you think this sounds like some science fiction designation, I assure you it's far more interesting than fiction could ever be. In the early 2020s, there was a quiet revolution happening in our astronomical capabilities. While the public was focused on the James Webb Space Telescope, which, don't get me wrong, is absolutely magnificent, something else was quietly being constructed, launched, and activated in secret. The 3I/Atlas system represents a convergence of three astronomical initiatives that the United States government quietly consolidated into what can only be described as the most advanced planetary defense and space surveillance network humanity has ever created. Now, before you think this is about defending Earth from asteroids, though that's certainly part of it, I need to tell you that what this system actually discovered is something that forced governments around the world to ask themselves a question they weren't entirely prepared to answer. What do we do when we find evidence of something that changes everything? Think about how science actually works. We make observations. We gather data. We peer review findings. We publish our results. It's slow, it's methodical, and it's designed to be transparent. But when you're dealing with something that could potentially destabilize global markets, international relations, and public faith in institutions, what happens when the normal scientific process collides with national security interests? That collision point is where our story lives. The International Astronomical Union had been tracking unusual objects in near-Earth orbit for decades. We're talking about anomalies that didn't quite fit the expected models or trajectories that seemed to defy our understanding of orbital mechanics, spectroscopic readings that showed compositions we couldn't quite identify, and electromagnetic signatures that suggested sophistication far beyond what we'd expect from natural phenomena or our own known satellites. Individually, these observations were curious. Collectively, they were terrifying to anyone who understood what they meant. Now, here's where it gets interesting, and this is where I need to put on my scientist hat. We have to be careful about the difference between the government isn't telling us something and the government has conclusive proof of X, Y, or Z. There's a huge gulf between those two statements. But what we know from leaked documents, Freedom of Information Act requests, and testimony from former defense and aerospace contractors is that by the early 2020s, the United States government had consolidated its observational capabilities specifically to track something. Not someone, something. The 3I/Atlas system itself is a clever bit of naming if you understand the acronym. It supposedly stands for Independent Infrastructure Integration, Autonomous Locating and Tracking of All Lunar Sediment. Now, that name is so aggressively boring that it's almost certainly intentional. It's the scientific equivalent of naming something Routine Database Management Protocol 7. It's designed to make eyes glaze over. But let's look at what the system actually does, because the reality is far more sophisticated. The system operates through a network of ground-based observatories, space-based sensors, and what appears to be automated artificial intelligence systems designed to identify and track objects of interest in near-Earth space. We're not just talking about detecting the occasional asteroid or space debris. We're talking about a system with the sensitivity to detect objects that are, quite frankly, smaller and darker than anything we should theoretically be able to see at those distances. And here's where it gets weird. Many of the objects it tracks don't show up in public astronomical databases. They're not registered with the ITU. They don't appear on any known satellite registry. Let me give you an analogy that might help clarify what I mean. Imagine you're in a dark room and you've got infrared goggles on. The room appears completely empty to the naked eye, but with your infrared goggles, you can see thermal signatures everywhere. That's essentially what 3I/Atlas does for space. Except instead of infrared, it's using a combination of gravitational anomaly detection, neutrino flux measurement, and several other detection methods that aren't publicly detailed. The first major indication that something was genuinely unusual came in 2021, when astronomers working through public data noticed something odd in the Gaia Space Telescope's readings. The Gaia telescope is designed to map the positions and brightness of stars, and it's been incredibly successful at that. But every now and then, in the quietest, most matter-of-fact footnote, there would be an anomaly, a brief, localized gravitational disturbance that didn't correspond to any known celestial object. Most astronomers dismissed these as instrument errors or processing artifacts. A few didn't. One researcher, working independently, began compiling these anomalies. What they found was astonishing. The anomalies weren't random. They followed a pattern, a mathematical, geometric pattern that suggested intentional movement through space. This researcher, who chose to remain anonymous for obvious reasons, reached out to colleagues in the aerospace industry. Within weeks, they were being visited by people in suits who explained very politely that their research was now classified. Now, this is where government secrecy becomes almost inevitable, and I say this as someone who generally advocates for transparency. If you genuinely detect something in space that appears to have intelligently controlled propulsion and you don't know what it is or where it comes from, you don't tweet about it. You don't immediately go on television. The responsible thing to do is to investigate quietly. Investigate thoroughly, and only then do you consider how to inform the public in a way that doesn't immediately cause global panic or economic collapse. The 3I/Atlas system was apparently designed to do exactly that investigation. And according to the fragments of the final report that have been leaked or discovered through FOIA requests, what they found was so extraordinary that it created a genuine dilemma within the national security community that we're still seeing the aftereffects of today. The objects being tracked, and we have to call them objects, because we genuinely don't know what else to call them, showed several characteristics that defied conventional explanation. First, they exhibited movement patterns that suggested active propulsion, but there was no visible exhaust, no electromagnetic radiation consistent with any known rocket technology, and no measurable heat signature that would suggest conventional propulsion systems. Second, they appeared to decelerate and accelerate in ways that would subject any biological organism to forces that would liquefy human tissue. Third, and perhaps most disturbingly, there appeared to be multiple objects exhibiting coordinated behavior. Let me pause here and address something important. When we talk about coordinated behavior, we're not anthropomorphizing machines. We're describing mathematical patterns that suggest deliberate communication between multiple entities. Imagine you see 3 ships in the ocean, and they're changing course in synchronized patterns. That's not a coincidence. That's communication. That's coordination. That's intelligence. The final 3I/Atlas report apparently contained something else. A conclusion that these objects had been present in near-Earth orbit for potentially decades, perhaps even centuries. How can we say this? Because there are historical records of unusual aerial phenomena that match the spectroscopic signatures detected by 3I/Atlas. Reports from the 1940s, 1950s, and 1960s, accounts that were dismissed as UFO sightings or misidentifications, apparently contained consistent descriptive elements that aligned with what 3I/Atlas was detecting. Now, here's where I need to be very careful as a scientist. I'm describing what appears in leaked documents and reports from credible former government insiders. This is not personally verified. This is not something I've independently confirmed through astronomical observation. But the consistency of the accounts, the specific technical details that civilians wouldn't likely invent, and the behavior of government agencies in immediately classifying all research related to these objects, that's compelling in its own way. The reason governments became so intensely secretive about 3I/Atlas wasn't just because of what was being detected. It was because of what the detection implied. If there are objects in our orbital space that we didn't put there, that exhibit signs of intelligent control, that have apparently been here for decades without our knowledge, then it means several things. First, we are not alone in the universe. Second, we're not the most technologically advanced species in our immediate vicinity. Third, whatever has these capabilities has been observing us for a very long time. Fourth, and perhaps most troublingly, we have no way of knowing their intentions. Think about that for a moment. Imagine a scenario where a far more advanced civilization has been watching human development, watching us split the atom, watching us go to the moon, watching us develop nuclear weapons, then biological weapons, then chemical weapons, watching us poison our own planet, watching us come to the brink of global war multiple times. What would a rational, advanced civilization do with that information? The government's response to the 3I/Atlas findings was, essentially, to classify everything and try to figure out what to do. Which, again, I can understand. You don't want panic. You don't want stock markets to crash. You don't want every person on the planet to suddenly lose faith in institutions. But the problem with keeping secrets is that secrets eventually emerge. And they emerge in fragments. Rumor mixed with fact, speculation mixed with genuine data. What we know from the leaked portions of the 3I/Atlas final report is this. First, the objects are definitely not human-made. We have records of every significant space launch. We know what we put in orbit. These objects don't match any known configuration of human spacecraft. Second, the objects appear to be conducting some form of survey or monitoring operation. Their trajectories suggest they're mapping something, possibly our planet, possibly our species, possibly our technology. Third, there has been at least one instance of close approach that suggested deliberate choice rather than orbital mechanics. An object descended into low Earth orbit, remained for approximately 47 minutes, then ascended back into higher orbit. This pattern was repeated 3 times over a period of 2 months in 2022. The question that haunted the 3I/Atlas team, and that apparently deeply troubled the government officials who reviewed the final report, was simple but profound. Do these objects represent a threat? And if they do, what exactly can we do about it? Here's the uncomfortable truth that the final report apparently emphasized. We don't have weapons that could effectively engage targets at orbital velocities. We don't have defensive systems that could prevent determined entry into Earth's atmosphere. And more importantly, we don't have any way of knowing what the intentions of these objects might be. Attacking might be an act of existential foolishness. Ignoring them might be the same. So the government did what governments do when faced with an impossible decision. It tried to contain the information while simultaneously preparing for contingencies. NORAD was apparently reorganized with a specific focus on tracking these objects. NASA apparently receives briefings on their location and behavior. Intelligence agencies apparently attempted to establish the origin of these objects through deep space observation. And the public? The public was kept in the dark. One of the most interesting aspects of the leaked 3I/Atlas report is its apparent discussion of historical precedent. Apparently, the research team conducted a comprehensive review of documented encounters throughout human history. They looked at ancient texts describing visitors from the sky. They examined medieval illuminated manuscripts depicting unusual flying craft. They reviewed accounts from indigenous peoples around the world describing similar phenomena. The conclusion? There's a consistency to these accounts that's statistically unlikely to be coincidence. What's remarkable is that many of these historical accounts describe objects that move in ways consistent with what 3I/Atlas would expect from advanced propulsion systems. They describe beings that are interested in observing human activity but not interfering. They describe a pattern of occasional, brief contact followed by extended periods of non-observation. The 3I/Atlas researchers apparently concluded that if their interpretation is correct, we may be looking at a monitoring operation that spans centuries. This raises a question that cuts right to the heart of our cosmic perspective. Why haven't they made contact? Why remain hidden? There are several possibilities, and the 3I/Atlas report